Hello, everyone, and welcome. Thank you for joining our first ANARI webinar. First, a couple of administrative items. Today's webinar will be recorded and posted on our website along with this slide deck. Please take a moment to answer the polls. If you have any questions, please use the Q&A panel at any time, and we will answer the questions at the end of the presentations. Today's speakers include Neil Trevett, President of the Khronos Group, who will lead us through a short introduction of Khronos, followed by Peter Mesmer, the ANARI Working Group Chair, who will give us an overview of the Analytic Rendering Interface, also known as ANARI. Then Jefferson Amstutz of Intel will give us a glimpse of the evolving ANARI API, and John Stone from the University of Illinois will tell us how to use the ANARI API. We'll save the last 15 minutes at the end of the presentation for an open Q&A. And with that, I'll turn it over to Neil. Neil?
Hey, Jeff, can you hear me okay?
Yes.
Great. So, hey, thanks, Jeff. I'm Neil Trevett, and I work on developer system ecosystems at NVIDIA, and I'm president of the Khronos Group. Firstly, I want to thank you all for coming today. We're looking forward to introducing you to ANARI and answering any questions that you may have. I'm going to start the session by briefly introducing you to the Khronos Group, in case you haven't come across us before. Khronos is an open standards consortium. We provide a safe place for the industry to cooperate and create interoperability standards. These standards enable applications to access the power of 3D graphics, virtual and augmented reality, and parallel computation. We're a non-profit organization, and all the standards that we create are open and royalty-free for the industry to use. We've been creating these open standards for 20 years and have almost 160 members. That includes everyone from the largest companies down to small startups. Any company who wishes to join Khronos is welcome to participate and have a voice and a vote in how these Khronos standards evolve. So you can go to the next slide. So here are the most active Khronos standards. As you can see, they group into related domains. On the right, we have standards such as OpenCL, Sickle, and Spear for parallel programming, and the OpenXR API provides portable access to augmented and virtual reality devices. But the majority of our standards on the left are for 3D graphics, including the new generation Vulkan for low-level explicit GPU acceleration, and WebGL that brings interactive 3D graphics and AR to the web. Khronos creates and evolves 3D file formats such as GLTF, which lets you easily transport and deploy realistic-looking 3D models and scenes wherever they're needed. The way that Khronos is organized, each of these standards has its own working group, which is where the interested members gather to define and evolve that specification. Most companies are active in 3D graphics, are already Khronos members, and so Khronos is a natural place to create a standard such as ANARI. And ANARI is Khronos' newest working group. ANARI is quite different and very complementary to the other Khronos 3D APIs such as Vulkan and OpenGL. Next slide. Move on to the next slide, Jeff.
It's there.
So Khronos working groups actually produce much more than specification documents, as any open standard needs much more than just a document. A good open standard needs conformance tests, adopters programs, educational materials to build a thriving ecosystem. As we mentioned, any company is welcome to join Khronos to participate in any of the working groups that are welcome to them. And we have a range of membership tiers to make participation accessible to everyone. All of our members can influence how Khronos specifications evolve and can accelerate their time to market through access to specification drafts and prototype implementations, often before they're made public. So that's the end of my brief introduction. And again, thank you for coming today. If after listening to the presentations, you think your company could benefit from participating in the ANARI working group and help us build an open standard that's good for the industry, please do talk to us. You would be most welcome to join. So next slide. So let me hand over to Peter Mesmer, who's from NVIDIA, but also the ANARI Working Group Chair. Peter.
Thanks very much, Neil. Hi, everybody. Thank you very much for joining the first ANARI webinar today. And after this brief introduction of the overall Khronos ecosystem, I just want to give you a brief overview of what ANARI is trying to accomplish. Before diving too deep, I just want to give a brief review of how we think about the scientific visualization application, which is kind of the driver of ANARI's mission. But even though we are driven by the needs of scientific visualization or analytic visualization, as you probably see towards the end of the presentation, we're by no means limited to it. But whenever you're trying to define a new standard, it's important to have a very well-focused scope. And we decided to stick to the scientific visualization as a starting point, because that's a place where we have a big need for a standard that helps us take advantage of modern rendering hardware. So when you look at the visualization system, typically you have some form of your data that you want to visualize. Ultimately, you want to turn this data into some kind of graphics, some visuals that can be either used to create new insight or otherwise to communicate the science that you're performing on this data. So you're starting out with this, this data set. You have to transform it, and you have to create geometry out of it. There's various pre-processing steps that need to happen typically. And then ultimately you get to the point where you have some objects in space and you want to convert them into pixels. So that's when you're trying to render this geometry. And this is the place where ANARI tries to solve a very specific problem. Next, please. The whole effort was driven by the arrival of new rendering technology, most notably by real-time ray tracing, and but also beyond that, just the availability of VR or other high-end rendering technologies. And so especially ray tracing can have a tremendous impact on the way that we look at scientific data. On this slide, you see on the right-hand side some reconstruction of the Earth's interior. And those are actually showing the same geometry, the same structure of the Earth's interior's wave propagation bulbs. And but on the top panel, this was rendered with ray tracing, whereas the bottom panel was just using standard OpenGL. And it's just striking the difference that that you're perceiving, the shapes that you can see that become very obvious with ray tracing, and the necessary ambient occlusion and global illumination, as opposed to the case of just standard rasterization. And so it's not really about making just nicer pictures, even though that's an important component as well for the outreach mission of science, but it's also about getting more insight into what's actually in your data. However, while there is a big effort, especially on the Khronos side, to come up with standards to make programming of rendering hardware portable and more accessible to a broader range of developers, writing a high-performance portable renderer on an API like Vulkan is still oftentimes beyond the scope of a typical scientific visualization ISV. As you remember in the previous slide, there's a lot of other stuff that needs to happen in a scientific application before you come to the rendering part. And oftentimes this other stuff is way more important and than producing the actual images. And so we're facing the situation that we now have all this power for doing advanced rendering, and yet those people that we want to cater to see just a lot of work, especially with different vendors providing different APIs to take advantage of this. And that's exactly where ANARI tries to strike. So the goal is ultimately to come up with a high-level API to simplify scientific visualization applications while leveraging the full potential of the available hardware. And this API should be platform independent and create portable code. Next slide, please. Just to give you an idea, a slightly different view of this challenge, in the situation before, right, we have the case where we have a bunch of scientific visualization applications, and each and every one of those needs to have a backend for OpenGL. They are probably in the process of rewriting this with Vulkan. They also need a backend for taking advantage of NVIDIA GPUs for ray tracing, or to take advantage of CPUs for ray tracing, or AMD GPUs. And so it just creates a lot of code bloat, a lot of maintenance that needs to happen. And it's not truly a nice separation of concerns, because, as I said before, oftentimes the rendering part is not the core mission of a visualization ISV. And so the goal is that with ANARI, basically all these ISVs can code against ANARI, and we have people who write backends for ANARI that take advantage of your specific platform. And so, yeah, I've listed the goals of ANARI here at the bottom, right? We have a common API, and it needs to allow you to build a description of the scene rather than talking about the rendering details. And the rendering details are left to the implementors of those backends. And on the right-hand side here at the bottom, you can basically see the stack of the software, right? You have the scientific application, or the visualization application on top, talking to ANARI. And then underneath the ANARI, we have renderers, backends that implement the standard, which in turn are taking advantage of platform-specific APIs. This can be portable APIs like OpenGL, but it can also be platform-specific APIs. And then ultimately, this sits on top of the available hardware. Next slide, please. This idea has gotten quite good industry support. Here is just a list of the organizations supporting the ANARI effort. What's particularly nice about this is that we have support from all across the visualization stack. So from the hardware vendors through people who develop rendering engines, visualization tools, all the way up to visualization applications. So that means that working together, we can really make this vision turn into reality. Next slide, please. Where are we? So back in November 2019, we had the exploratory group. Neil can tell you everything about the process of bringing an idea to Khronos and then becoming a working group. But so we started last November with this exploratory group, where we just tried to figure out, is there a need for this kind of a standard? And then on March 3rd, we turned into an actual working group. So ANARI is brand new, but I think we've already made quite a bit of progress, as you will see in the following presentations by my colleagues. But the current timeline sees that somewhere towards the end of this year, we will hopefully have a provisional specification of the standard, and then have a final version of the first ANARI standard mid next year. And that's also why we're really keen on getting your input now. I mean, now is the right time to help us define the API in a way that makes it most useful to you, either as an ISV who wants to write analytic or scientific visualization applications, or as somebody who wants to write backends that can take advantage of whatever features and hardware is out there. Next slide, please. Progress so far. So the goal was that we, again, in order to focus our activities, we looked at the variety of different use cases and said, for this provisional first standard, and then for the first version of the standard, we should have a set of use cases that need to be covered. So we then looked into a list of existing APIs that are out there. Anyone who has tried to come up with an API themselves knows that it's really hard if you start with an empty piece of paper. And so we wanted to have inspirational APIs and said, okay, this is a good starting point. Gets us whatever 80% to where we want to be. So let's start with that, and then start to twist some knobs to make it into ANARI. And so we selected our starting point. And since then, we've basically started to develop exploratory implementations, just to see if this whole idea of this ANARI story can actually go all the way across from the application to the platform-specific optimization. And so we now have draft prototypes for the major hardware platforms out there, for CPUs, for GPUs from AMD and NVIDIA. We have an OpenGL backend and a USD backend, just as a yet another type of emerging standards that especially other parts of the industry are interested in. So we have on the backend side a broad variety, but then also on the front end side we have with VTK and VMD two widely used applications in the scientific visualization space that have some draft implementations on top of ANARI. And so we're exploring that, what features are missing, which features need to be adopted, and what capabilities are still necessary as we go. And so to give you a bit more an idea on how to progress from here, please go to the next slide. I'd like to introduce you Jefferson Amstutz from Intel, who's giving you a glimpse of the evolving API, mostly from the perspective of the backend side. And with that, Jefferson, please take it from here.
All right. Thank you, Peter. So this is really going to be a glimpse because there's a lot of technical details to talk about, but we can't, it's going to be difficult to cover all of that in 10 to 15 minutes. So I'm going to do my best to whet your appetite for what we're working on. And hopefully as people participate, they can come and provide some input onto where we're going. So if we go to the next slide, the overall technical mission statement of what we're solving is to create a viewport rendering API, which is exactly not a scene graph. And this is a question that's come up multiple times, but the goal here is we want to commoditize how you talk to an existing rendering implementation, not take on the whole problem of domain and application specific structural relationships and queries and traversing that for non-rendering purposes, metadata. All of that's very difficult to unify. So our mission is small, but very intentional to maximize the application surface area that we can cover for rendering. Another important aspect of ANARI of what we're working on is that it's unidirectional. There are some notable exceptions, but for the vast majority of the API, we want to have data flow from the application then into the ANARI backend. So this gives a lot of freedom for implementers to do creative, interesting things with their backends. And I think this is most demonstrated through different, wildly different execution topologies that I have some examples listed here. On the far left, we have the very common case where we think of a single process application on a single machine that talks to the ANARI API that is implemented with a particular backend you're using that eventually gets on GPUs and CPUs, et cetera. While this is super common and obviously a huge portion of what ANARI is going to provide commoditization for, there's some other more creative implementations that we want to always keep the door open for. So in the middle, you could think of a single process application that that talks to the ANARI API, where the implementation then can distribute this to multiple nodes in a cluster to do compute scaling. And so in scientific visualization, we often are working on HPC machines, or you could even think of creating a cluster out of commodity hardware yourself. That this is something that ANARI, with the right semantics of the API and the right API design, can trivially enable without making assumptions about application structure. And then, of course, the last one is pretty forward-looking outside of scientific visualization, but we do find lots of cases where distributed applications that are already distributed MPI cluster applications could all collectively talk to ANARI, and then ANARI could render all of the data spread out on all of those different nodes together in a single image. That's a really interesting use case for distributed rendering to also commoditize that. So if we go to the next slide, the core of the API is C99. That's what we're working to standardize. With C++ bindings, we can get convenience and type safety back, but we're going to focus on a C99 core API standard. And then the bones of this centers around two things: opaque handles to objects that represent the different actors that participate in rendering a frame, and then parameterizing them with named parameters with a string name and then a particular type and value associated with that. But at the end of the day, the entirety of the API is built to serve one API call, which is ANARI render frame, which is what I have listed here below. Everything we're doing is really centered around making an image, a 2D image of 3D data specified by the application. So if we can take a particular device implementation of ANARI to populate a particular frame buffer using a particular rendering algorithm, a camera vantage point, and the world we want to see, and that all of this is wrapped up to be non-blocking as to not block the calling thread with this. So it's a lot in one call, but just if we focus on this, we know what we're serving for the rest of the API. So if we go to the next slide, another aspect of this is to how do you parameterize objects, and we can actually do this with one central API call, which is that ANARI set param, which is there in the middle of the screen, where we take a live object handle. Remember, this is one of the actors in the API. We provide a particular parameter name, and then can set a type that is associated with that and the particular value that comes from the application. And the strength of this design is that it does not strongly prescribe things like short vector math libraries above the API. We can compose with all kinds of different application existing math types. So an example at the very bottom of the screen is like a GLM vec3 that we want to express like a camera position. And so we can trivially compose with GLM using something that looks like a vec3f in memory, like a GLM vec3. If we go to the next slide, we have a list of, not all of them, but a lot of the handle types. What are the actors that participate in rendering a frame? What we call a device is a software device. This represents everything that a vendor might provide. So it represents like what all of OSPRay would provide, or NVGL, or these different implementations we've talked about. And so everything else comes from a particular device implementation. Buffers and arrays are very fundamental because they represent memory that comes from the application. Buffers encapsulate memory ownership. So this could be copied from the application, moved from the application to ANARI, or ANARI owns the memory and then the application populates it. But with arrays then provide type information that and interpret that memory, of course. So we solve both of those problems with different handle types for those specific issues. Frame buffers are the output that come from ANARI, the pixel information, depth, accumulation, etc. Renderers represent the rendering algorithm, so the lighting model or shading model that are associated with the particular algorithm that's being chosen to get a particular look from your device vendor. Cameras are the vantage point, the projection from world space into image space. Image operations are the way we can attach things like pixel denoising or tone mapping with the asynchronous frame render. So the reason this is in the API is if we have an asynchronous frame, it may be desirable to have things like denoising also be asynchronous and a part of that frame render operation to make sure that phase also stays decoupled from the calling application thread. Then we have things like materials and other appearance objects as well. But the world, I'm going to drill down to very specifically because it's a very core part of how you think about rendering a scene is how do you define the world. So if we go to the next slide, this is a high level view of everything. It's single level instancing right now, which is you have a world with instances. Instances contain objects that share a local coordinate system, but we're going to go from the bottom up to describe what each one of these mean. So if we go to the next slide, we start with geometries and volumes. This is the raw scene data itself. So geometries are surface information with any kind of representation a surface can be defined as. And then volumes are scalar fields that can be sampled, which also have a diverse set of structural representations. On the next slide, we decoupled that structural and surface information from their appearance. So for geometric models, this represents the surface and the material information that is encoded on that surface. And for volumetric model, it is the appearance information associated with the volume. So this would be something like a transfer function to apply an opacity and color to particular sampled values from the scalar field. On the next slide, we also have lights. This is where illumination comes from. It's depending on the rendering algorithm, might have different interpretations. Some rendering algorithms might actually throw this all out. Some might only care about lights that are defined in the scene. But at the end of the day, to define illumination from the scene definition perspective, they are siblings to geometries and volumes. Then on the next slide, all of this wraps up into an instance that takes this local shared coordinate system of all the objects in the instance and provide a world transform for then where it goes into the world. So if we go to the next slide, it's everything together. This defines everything that goes into the world that gets rendered. I will note that the array brackets that you see represent array relationships. So a geometric model has a single geometry, but an instance would have up to n geometric models. So this is how we don't necessarily say that one geometric model can only exist in one instance, but it exists in an array that goes on the instance, if that makes sense. So you can have more than one top level world that contain different instances. Those instances can be in any top level world. It all depends on what you're going for in your application. So if we go ahead on to the next slide, we can talk about what are the current implementations that we have that we're working with. And our current approach is to focus on, let's get some implementation experience, and then from that experience, we'll write the specs. So we're starting with a shared common front-end library that takes API calls and translates them into different device backends. And then we all, as implementers, then implement these different device backends according to the objects that were given to us. So we have different ray tracing implementations and an OpenGL implementation. There's more on the way. There's actually a lot of activity going on right now. And so I have some simple examples here that come from VMD, a live application that's got some early work with ANARI. And the note here is that we're all viewing the same scene, but each backend, NVGL, OSPRay, ANARX, and of course, the original rendering code that's baked into VMD, they're all showing the same scene, but they all have these different lighting trade-offs. They might be using different hardware, and that's okay. Like that's what the vendors, that's what an implementer of ANARI provides. This is the goodness that I can provide you, but I didn't make you use an entirely different API to tell me what the scene is. So it's actually very intentional. These look subtly different with different lighting and different trade-offs and different hardware. But lots of activity. If we go to the next slide, I just wanted to also whet your appetite for the things that you can do with ANARI. This is very scientific visualization focused, and that's okay. That's a lot of our folks participating right now in the working group come from SciViz, but with the right materials and illumination models, like this is an image of OSPRay with some car paint materials and global illumination path tracing and the Disney BRDF, we have a material implementation of that. At the end of the day, the components that go into making that world, defining materials, geometries, volumes, etc., they're very applicable to general rendering problems. So if we also go to the next slide, even combining surfaces and volumes with global illumination, and ANARI is not prescribing scientific visualization. What we're doing is making sure that scientific visualization is not designed out of the API itself. And so when you see John Stone's coming examples that are all focused on scientific visualization, just know that when you look at those images, they'll share a lot of illumination characteristics from other domains, which is good and intentional. So with that, we can go to the next slide. I'll introduce John Stone, who's going to talk about the ANARI API from the application perspective, as well as show a diverse set of examples that highlight the kinds of things that you can do with ANARI.
Thanks, Jefferson. Next slide. So like Jefferson already said, our goal in the design of the API is really to keep the API design open to support all of the features we need for scientific visualization. We don't want to constrain our design so that we eliminate anything from other areas, but we have to remember first and foremost that we're after the needs of scientific and technical visualization. So that means we have specific needs that I'll declare here in a coming slide. But one of the things we're also after is to make it easy to adopt the code. So to give an example, in my software VMD, there are maybe something like, I have 15 different rendering interfaces built into VMD over a period of maybe 25 years, which even predates my involvement. And so if you think about all the lines of code that are associated with that, there's something approaching 80,000 lines of code, even for relatively simple file-based renderers. And that's a lot of work for any application developer to undertake to support a bunch of different rendering backends, whether they're live or even those going through files like I was describing. What we're after, we want, first of all, live renderers. So we want very high performance. We want interactive rendering. We want to support a bunch of things that are unique to SciViz. We want to make those renderers easy to use. We have to gloss over, as Jefferson already said, in places differences between the way the different renderers work and the way they like to operate internally, the memory spaces and hardware they use. And we want to provide easy to use development tools so that an application developer can get started using ANARI very easily, and they can basically buy into successively more sophisticated means of using the APIs. To support that sort of on-ramp, we are developing API tracing tools, tools for debugging the API calls an application makes. And by collecting, recording, and replaying those, then it makes it a lot easier to try different things with different rendering backends. We already have early versions of those tools developed now, which is very exciting. We want to be able to use state-of-the-art rendering techniques. This is probably the major thing. As computer graphics technology has gotten more sophisticated, hardware has come along by leaps and bounds. The effort required to stay in sync with the state of the art has gone up dramatically. And that's sort of what both Peter and Jefferson were pointing out. And we want to encapsulate that difficulty in this portable API and allow people to achieve very nearly, hardware constrained performance while also having an easy to use API. So that's a tight rope we have to walk. And so what that also means is we're not doing everything. We are going to keep sort of distractions out of the ANARI API. There are lots of things that potential application developer might ask for that are sort of domain specific features or things like this. There are going to be lots of opportunities to put those things into middleware that then sort of lands in between ANARI and the application. And so we are not attempting to address all of those issues. We have a very focused mission, and to achieve our performance and hardware platform goals, we have to keep on this narrow focus. Next slide. So, what are the needs of SciViz and technical visualizations? A big part of what we want is to support what we think of as analytical visualizations. These are visualizations where we have three-dimensional geometry typically, but we also have the need to display legends, tables, data, numeric and qualitative of various kinds. These could be things arising from simulations on supercomputers or workstations, but they could also be experimental data, things like microscopy, tomography, various other types of imaging data, medical imaging data even. Wide variety of things. This means there's going to be some diversity in the types of geometry, different primitives we want to support. We do care a great deal about things like supporting time series, and there will be a diversity of different material properties, texturing, and color transfer functions that different applications are going to need. And so ANARI will have to bridge that gap and support the things that are most broadly required by the SciViz applications. So some of the things we hope to get out of the backends then, what they bring to the table is the state-of-the-art rendering techniques, things like path tracing, ambient occlusion, lighting. These are things that if you had to start from scratch writing a reasonable hardware accelerated ray tracer, even using some of the low-level toolkits that the hardware vendors provide, if you had to do this yourself, you're looking at writing maybe 12,000, 15,000 lines of code just for a reasonable renderer. Doing the same thing with ANARI, you know, I would say in my prototypical implementation of VMD, we can get this down to just a couple thousand lines of code to achieve a very large fraction of the same functionality in a much easier way. And so this is very exciting. Next slide. So this pictorial sort of represents, you know, I wanted to give some visual examples. We're not just after molecules or computational models or any particular one domain. There are lots of opportunities for us to use these advanced visualization techniques, ranging from experimental imaging to sensor data, LiDAR, things like this, large databases, or you could imagine InfoViz type things sometimes have an opportunity to use these kinds of rendering techniques. Right now, we're sort of exploring this territory, and this is a key area where we'd love to have feedback from users where they see an opportunity to exploit what we're doing for their domain. Next slide. One of the jobs that the application has to undertake then, since ANARI will relieve the application of having to worry about low-level rendering details, one of the key things the application is going to have to keep track of is doing a little bit of matchmaking. You can imagine that not every renderer will provide the same visual styling or may not have all of the same rendering features. Some of the things we're talking about doing as we develop the spec are to add feature profiles so that you can have groupings of commonly needed things together. And you might be able to say, I want to use only renderers that support the particular kind of volume rendering I need, and maybe the volume rendering features are collectively in one of these feature profiles. That would make it very easy for an application to identify just the backends that are good candidates for what it's trying to do. Maybe they support structured volumes of a particular type, or they support a particular material properties, things like that. That'll be something that makes that easier. One of the goals we have is that by design, you know, the application can use a wide diversity of future released renders. You know, you shouldn't have to rewrite your application to exploit a new render. If somebody develops a new ANARI backend, we should be able to use it without much difficulty. And to be able to do that, we have this matchmaking process. And that means that the application can dynamically query all the properties of the different backends, the different features they support, what geometric types, shaders, and so on that they might have. And in fact, in some cases, going beyond what ANARI provides itself, we do envision that some renders might provide sort of vendor-specific extensions that can then go further. Next slide. So just to sort of show you the benefits of these things, to look on the left, if you wrote a classic visualization code sort of straightforwardly, you'd get simple lighting like you see on the left. This is a satellite tobacco mosaic virus. The same thing, just rendered with ambient occlusion lighting, elucidates tremendous structural information. So you see pockets, pores, cavities that otherwise wouldn't be easy to see. Looking on the far right, you see more of a conventional way of rendering the same structure in VMD. So this is kind of the value of these rendering technologies brought to SciViz. Peter gave some more examples, and I'll show you some more as we go on. Next slide. So these are more further examples. You can see that just by applying state-of-the-art visualization techniques, the visualization practitioner can exploit human visual intuition to call attention to key structural details, to let the viewer see different spatial relationships, complex geometric structures. A lot of things are a lot easier to see. And, you know, just like a photographer composes a scene to tell a story or to bring your attention to something, you can use these techniques to make better science communication figures for journal papers and so on. Next slide. So here's another example showing a climate simulation. You know, this is sort of a typical use case. We want to enable tools like ParaView and VMD and many others to be able to, just by turning something on, get a high fidelity rendering using the same data and the same application that scientists are already familiar with. You know, many of these visualization applications have decades of development. And so by using ANARI, our goal is to really bring state-of-the-art rendering and interactivity to these legacy applications at very low cost. Next slide. And this will enable the scientists to use these tools immediately to do their work. And this, you know, this is everything from their daily grind, what should I say, 9 to 5 visualizations that they need to do to elucidate the intermediate results of some calculation, all the way out to their journal figures, cover images, and things that are more public outreach oriented. Next slide. And so to give you an example, you know, I've done some work with VMD on planetarium dome visualizations and public outreach type materials. Here you see examples of VMD coupled to a camera pre-visualization tool that's developed at NCSA. While, you know, we use ray tracing in VMD for camera flight paths and planetarium show planning, it's better to use a different tool for that. This would be a great opportunity for both of us to adopt ANARI. It would enable different interchange between the applications to be done more easily. And, you know, we don't expect that all renderers are all ray tracers. There are plenty of cases where rasterization is useful for the camera flight planning. That's a great example. Next slide. This is more of a typical visualization in NCSA's virtual director tool. There will be plenty of cases where we want to draw things that are more vector graphics oriented, and we expect that ANARI will help address those types of things too. Next slide. And, you know, the key things that we're after with SciViz and are things that, you know, other APIs aren't really designed for these things. We have to meet some needs that are special to our community. And so while we're not excluding the other things that we might do with the API, these are things that we have to sort of design in. We have to be very careful about our API design choices so that we enable live view of huge data sets. We need to have very low overhead APIs. We need to support asynchronous rendering so that we can do better overlapping of compute and visualization. We want to, as Jefferson already pointed out, support distributed memory rendering and other special cases. And that just means very careful application API design and doing things like zero copy and things like this. And so these are all things that we're concerned with. Next slide. And if we do those things right, we'll be able to do huge scale, you know, there we go. We'll be able to do huge scale visualizations that are, you know, capacity constrained, you know, with terabytes of data. Like you can imagine large climatology visualizations that, you know, have massive data sets where we have to calculate streamlines, do volume rendering. There are lots of opportunities here. Next slide. And these are just a sampling of some of the things we want to be able to do. Here you have very sophisticated path tracing and lighting applied to typical flow visualizations. So these are great opportunities for applications to use ANARI. And with that, next slide. I'd like to basically invite everybody to become involved in the ANARI development. You know, the working group, as we have a lot of experts in rendering and parallel computing in the working group already. One of the areas where we need more feedback is more domain-specific input from developers of applications, but we welcome anybody who's interested in working on the API design, you know, application development tools, rendering backends, and if you're interested in getting early versions of ANARI working in your own software, whether you're writing renderers or you're writing applications, there's a great opportunity for you to become involved. So these are contact information. You can contact us about getting, you know, either joining the working group or giving your feedback to the working group on the things that you've heard about today. And with that, I'd invite Peter and Jefferson and Jeff Phillips to go ahead and join us, and then we can answer your questions.
Thank you, John. Let's go with a question first for Jefferson. Jefferson, what are the exceptions for the unidirectional flow picking objects?
Yeah, right now it's picking, and the only other one would be being able to query world bounds from objects in the world. Both of those are not locked in as required right now.
Okay, and I have another question for Jefferson. How is world not the same as scene graph? You need to order your objects and control them in any Viz app. So how do you deal with that in this context of ANARI?
Yeah, this is a very large question, so I'm going to do my best to bring it down to the core things that distinguish ANARI from a scene graph. And when I say distinguish, we're actually part of what a scene graph should solve, but just a very small part of it. Things ANARI are not solving that scene graphs would be responsible for would be like file I/O, loaders to and from disk of different file formats, data filtering. So thinking like the visualization toolkit, a lot of it's built around transforming data from one form to another, like even without rendering involved. Things like UI metadata, being able to display the structure of the scene in some type of interactive interface. Distributed applications that need to talk to itself like a simulation that, again, not rendering related. Being able to understand what the data was that was set. So ANARI takes a perspective of, if you set this value on this object, you obviously know what that value is. And if you have a specific place in your application where that came from, that should be the place that you go look for that information. And then like object update queries, where if you modify an object that you have created for ANARI, that you are also the one that knows that you needed to update it. So then you also are the best person to track that information for other non-related reasons. So if you sum all those together, it's a lot of things that then ANARI is not trying to create a universal solution for. There are a number of great packages out there that solve those problems. They just does that all differently and typically tailor to particular domains, that once you get to the rendering portion is what looks largely the same and what we're trying to standardize.
Yeah, I would just add one thing there and say that that's a great example where historically VMD has always had to use its own internal scene graph anyway, because the ones that are out in the public scene graphs like OpenSG and so on, they're not well suited for the needs of molecular visualization. So that's another reason for us to stay on the sort of the rendering side of that equation and leave it to the application to decide which scene graph or what structure they would rather use.
Wonderful. Peter, how do you place ANARI on the portability versus performance scale?
Yeah, I mean, at the end of the day, it is about fast rendering, about enabling people to have live visualizations. And so performance is definitely one of the foremost topics. But as I introduced at the beginning as well, being able to take advantage of modern hardware from whatever vendor is another key element. So yeah, there is the trade-offs here. And the idea is that we're providing a good implementation by default for all the different backends. And then as John mentioned, there can be hooks or individual buttons within the different backends, so that there can be extensions for individual backends that allow you to tweak performance even more. But the goal is that the standard implementations for the backends offer solid high performance on all different workloads and all different platforms. And maybe just to tie back into the previous question a bit, right? When we say that we're solving a similar problem or a sub problem of the scene graphs, the idea is not that if you have your own scene graph that you need to copy anything into the ANARI data structures. ANARIs can live with data structures that were given to you by your scene graph.
Yeah, absolutely.
So that helps again with the performance in order to make sure that we have ultimate performance.
Wonderful. I think this one would be for Jefferson. You haven't mentioned Microsoft DirectX. To be fully compatible, a Viz developer would want to know if this will use the fastest rendering backend for Windows. Is DirectX team involved in ANARI?
Yeah, great question. So ANARI is trying to define, or it is defining an interface to an existing rendering implementation where any lower level graphics APIs are entirely up to the implementer of that particular ANARI backend. So for us, DirectX would be a great candidate for someone to implement an ANARI implementation with it, but the ANARI API itself is not at all tied to any of these lower level graphics APIs. So there could be there could be multiple DirectX implementations. The idea is there would need to be a vendor, i.e. someone who wants to be an implementer to use DirectX to implement ANARI, because ANARI itself does not ship any production backends to be used, to be expected to be used by application developers. So just like we have a OpenGL implementation, there could be other OpenGL implementations that have different subtle trade-offs. Same thing with like using Embry or optics underneath the hood. These aren't mutually exclusive. There could be multiple optics backends, multiple Embry backends, multiple DirectX, multiple Vulkan. It all depends on who's writing a renderer. That's their underlying tech, then is their implementation detail. Hopefully that makes sense.
Yes. So will ANARI have bindings for C++, Fortran, Python?
So with C, we think that that's probably the best bang for your buck to get all of the compatibility with other binding to other languages. We don't have an explicit goal to enumerate all of those, but we found in practice with other C-based APIs to things like bindings to scripting languages or things like Fortran, it is the easiest done when you're working with a C API. And so that's why we've chosen that.
Okay.
And maybe just to add to this one, I think that's a very good question, that this is exactly the type of audience that we're also trying to cater to. Right? If you already have a super duper renderer that takes advantage of all different platforms, well, there's probably no need for bringing ANARI into that. But if you're writing in the Python ecosystem, if you're writing, if your focus is mostly on the Fortran side, and you want to get a high performance renderer that can take advantage of arbitrary backend rendering hardware, that's the place where ANARI can hopefully solve a lot of problems for you. But that's exactly why we also have this call for participation. We want to hear from you. What are the problems that you're trying to solve? How could ANARI address the type of workloads that you're interested in?
Wonderful. If the goal of ANARI is essentially to render a single frame, how are the time series going to be supported?
It's a great question. I can take that one. So that there's multiple answers here because there's different ways time series come about. You've seen in OSPRay's public demos over the years, a lot of sci-viz cases we've dealt with time series, that every time step is its own separate world. Those worlds could share like common geometry, but usually if you have like a time series of like a volume CFD simulation, that every time step ends up just being its own standalone world. And so for each frame, you're just selecting through that series of worlds for which time step you want to render at one time. There's others where you could be updating data in place. Like if you have some particle simulation and you want to update all, you want to represent those as spheres, you could update all the sphere positions in place. That has different trade-offs than trying to create copies of that data, so you can go through time that way. But the idea is all of the above is something we want to support, but individual worlds in sci-viz tends to be the most common, but it is certainly not the only way that time series can be represented.
Okay.
I could just add a comment. Like you could imagine if you were doing something with a city scale visualization, you had a car driving through the city, like Jefferson was saying, there's an opportunity for some data reuse there, or keeping large amounts of the world shared across multiple time series. That's something that we definitely care about. And there's also, you know, one of the things we've been working on is figuring out how we would interface ANARI to other types of sort of unusual rendering systems where we might need to cache time series through various tricks in a rendering backend. And that's something that people are exploring right now to figure out how they would do that for some of these special rendering systems. I'll just leave it at that.
Okay. Peter, can software based on the current ANARI headers be developed in the open?
That's an interesting question. I mean, sometimes there's not a lot of software or tangible products being released while the standard is being developed, and it's definitely not the case that that whatever we have as headers at the moment can be viewed as a pre-release of the standard. It is work in progress. It is something that can change at any time. On the other hand, we're obviously very much interested in seeing people starting to use it and also give feedback based on those tangible artifacts that have already been produced. And so we've actually just checked with Neil, and luckily we have him on the call here as well, to make sure that this is in sync with Khronos's philosophy. And it sounds like we can actually release those headers, and as a consequence also some of the backend, as long as it's clear to everybody that, yeah, this is by no means a preview of the standard, but rather this is the work in progress that we're currently doing. It is as is, and as we said, the final standard might look completely different, but we're more than happy if people start using it. We're even happier if they also come and join the working groups and start participating to actively influence the way that we're defining the this interface.
Yeah, I would volunteer to say that, to give you an example, and I've had ANARI implemented in VMD for a while. If you're going to be using something that's in flux, you should be expecting to periodically have to rewrite a couple thousand lines of code, or at least do global search and replace on a frequent basis. So, and I would say that, like Peter brought up, really, you should join the working group. It's not that hard to become a member. And I think that anybody who has any questions about that, Neil can get them sorted out.
Okay. Is there a hardware optimized ANARI backend for ARM?
Not yet. Not yet, but some of us do have access to some bleeding edge ARM hardware, and that should be a fun thing to see in the coming future here.
It should also be mentioned that we do have an OpenGL backend, and so if you have an ARM platform that has OpenGL support, it should work on this.
So could someone with a customized GLSL shader, can they use that in an ANARI renderer?
So I'll take that one, and I think the answer is it's a conversation with, as an extension with a particular vendor device implementation. So, like for instance, OSPRay being a CPU ray tracer that doesn't have anything to do with OpenGL or any GLSL underneath the hood, we probably would never implement that. But if someone like NVGL, I don't want to sign up NVGL for that, but if someone was using OpenGL, it'd be reasonable to say, hey, if you want to get very specific with programming my internal implementation details, you can give me a string of GLSL source. Obviously, use at your own risk. And the idea is ANARI is trying to specify a standard interface for how that interaction happens. And obviously, we want to specify what are some core features that every implementation has to provide to be compliant, but leaving the door wide open for interesting things like accepting GLSL source, OSL source, Material X, node graphs, all kinds of stuff. We want to be able to handle all of that without inventing tons and tons of API calls to make that happen. I think that's the direction we're going.
Okay, and I have one last question. Will ANARI work on mobile?
So I'd say the participants in the room, we don't have any active mobile users. The one thing we've identified is issues of assuming 64-bit addressing, which on mobile would be the highest chance that you would be in a 32-bit or less environment. That said, there's nothing else. It ends up being, is there a renderer implementer, a vendor who is targeting mobile? If that is true, then ANARI absolutely should work just fine. There's nothing dissuading from that platform other than who's participating in implementing the API.
Yeah, I think the way to look at that is tomorrow's cell phone is going to be as powerful as today's desktop workstation. So, you know, eventually it seems inevitable that will make its way down.
Wonderful. Thank you, gentlemen. Just a reminder to everyone out there that this has been recorded, and we will share this presentation so you can share it with your colleagues along with the recording. And thank you for joining us.
All right. Thanks, everyone.
Thank you.
Thanks, everyone.